Welcome everyone to Robot Builders, DPRG's Robot Builders Night Virtual for 10th of September. We will do the usual roundtable followed by open mic. This meeting, some section of the group will likely drop off at 8 o'clock to go and watch a significant television event. But we will leave recording going for anyone who, for those who stay on, and I will be back after 90 minutes and take care of closing up the meeting and finishing the recording. We are recording it, so if you don't want to be recorded, go on mute or blank your camera. With that, we have, I don't see Tom on the line yet.
Not yet.
So then I'm going to go next and share a little update that just get the right tab, which, as luck would have it, is on a different window. So sorry, just a momentary. Okay, here we go. So this is the version 3 of my bumper, done in Onshape, and I retained the original concept of having two halves, a half bumper and a half frame, bumper frame, and a rod that pokes through, and then you join these two halves with bolts to make a whole thing. And so I went further than previously. It's some design changes after a design review with John, and mounted some micro switches on it, and the pistons and some springs. And this is real handy because it let me check. Okay, so the springs poke out the front, but John pointed out that my bumper was very fragile, and so I beefed it up and got these micro switches. So this was sort of an interesting new thing for me. I got a CAD model off of DigiKey and imported it into Onshape, and so anyway, the idea is sort of pretty obvious. I'll put a pin through there at an appropriate place to stop it from popping off the front, and this bit just gets duplicated and bolted on to its neighbor, and this frame gets duplicated and turned around by 180 degrees, and then where you go. So anyway, that was my what I've been working on for a little while, and I think that the thing that I want to say about it is that modeling it as an assembly this way actually helped me discover some problems that I wouldn't have found till I built it. Like I had the end of the frame was too short. Well, the frame was too short, and these tabs that bolt onto the partner frame were right up against the terminals of the micro switch. And then I hadn't realized it, but the micro switches needed to point in opposite directions, so the holes needed to be mirror imaged. So things like that were, and oh yeah, I'm glad I modeled this as an assembly and put it all together before I tried printing it. So I think I'm pretty much ready to print this thing. So that's very exciting. And
what are your rods made out of?
What? So I've got some Delrin. So I hope that, Delrin is kind of greasy or slippery kind of stuff. So I hope that it'll slide through the holes properly. And I guess the other big news is I've resisted for a long time, but I now am the proud owner of a 3D printer.
That's good.
Haven't unpacked it yet, but that's going to be next up. So
welcome to a whole new series of challenges and frustrations.
Well, yes, and it's all rather concerning because there's very little time left before Roborama, when I'm not, I'm going on another 3 trips before Roborama. So
I didn't catch the printer. Was that an Ender printer? I didn't catch the model.
Yes, what's the model?
This is the Ender 3 V2.
Fantastic. I will tell you right now, you will want to get the gyres firmware updates, and you want to get either the silicone bed offsets or the yellow upgraded springs. And if you want to go for a ABL, automatic bed leveler, you would be doing yourself wonderful favors if you do those 3 things.
Or yellow spring bed leveler. And what was how'd you spell that first word that you said?
Don't even remember what the first word was now.
It's the gyre or something.
Yeah, gyres, JYERS. It's a
is
firmware update that you update the firmware inside the controller, inside of your Ender, inside the printer. And there's also a controller that is the screen, has its own control stuff, and there's a process for doing that. And if reach out to me, Paul, I'll send you a video. BV3D is a cat out of San Antonio that does a really nice video of how to update all that stuff to gyres. You get better looking icons, you get more capabilities than what the Creality firmware gives you out of the box.
Yeah, but the basic will work. So
yeah, John is absolutely right. The basic will work, but I've just found that I got it's an easy enough thing that after you print a benchy, your first print, you say, "Oh, that's cool," and you want to do more. Want to get to that, and the Creality, it's about $40 for the Creality Auto Bed Leveler. Is not necessarily a must-have because you don't really need it, but it makes your life a whole lot easier.
So which version you get? Because I was going to say mine came with it, so some of them have it already.
If he got a V2, he probably doesn't have an ABL on it. If he got a V3, he certainly does.
Yeah.
Because mine does, and it's the all level is definitely it's nice.
Yeah, you don't, and John is everything that I just said, and everything John said is totally legit. Out of the box, the thing prints. It prints nice. But if you don't, you don't need all those things. But if you want a better experience, I would do those 3 things.
Thank you very much for that guidance, Harold.
Yeah, I'd second that, but I'd say don't do them all at once, because then if something breaks, you don't know what it was. So work your way into it one step at a time.
So I would say I vote for the all level first of the bunch.
I'd agree with you, and I'm going to agree with John too. And I am the world's worst about when I see people come online and going, "Hey, I got my new printer and it doesn't work," and they then get around and suggest $400,000 in upgrades, and like you only spend $100 on my printer. Cut it out. Make the printer work first, right?
Yeah.
Well, did you buy your 3D printer locally or did you buy it from overseas?
I actually took advantage of Doug's spare that he had sitting in his closet.
Oh, fantastic!
Really locally?
Yeah, really locally. Just picked it up yesterday.
Oh,
I was going to say, I don't know if Micro Center is closer or not from his house, but
So anyway, that's big.
it may have been
news,
cheaper than
exciting.
Micro Center.
well, definitely cheaper than Micro Center. That probably is true.
Okay, that's all I had. Pat, you're up next.
Okay, so I've been playing around with a little Make-Sense A010 3D sensor or 3D sensor, I guess, or time of flight sensor. And I've had a little bit of trouble getting it going. I finally got it going. I had written up a Python script, and it was hit and miss whether it was working. And I had it working last time I demoed it on the meeting, and then I passed it on to Doug, and then I tested it the next day after passing it on to Doug, and it wasn't working. And I thought, okay, so I did some troubleshooting. Anyways, I ended up grabbing one I found on MaxSense site and modifying it. It's in Python, and I've got it running on the Raspberry Pi. But what I'm disappointed in is the latency I'm getting in Python. And I'm assuming it's the OpenCV and running Python on the Pi. I'll share my screen and show what's happening. So everybody can see my screen.
Yep.
So I've got it in 25 by 25 mode for pixels. And 5 frames per second. And basically this is the image I'm getting out of OpenCV. And as I run my finger past the sensor, I've got about a 1.5 to 2 second delay as it's going by, which is like not that usable for a robot. And at this point, I'm not sure if it's a Python OpenCV thing, or should it possibly convert it over to C++ OpenCV. I have a feeling that C++ would probably run substantially faster. My C++ programming is not phenomenal, especially with dealing with serial ports and stuff like that. I'm in the process of looking at it and seeing what I can do to try to pull the image out and work on it with C++.
What's your CPU usage? Is it like, is your Pi fully loaded right now with this?
Let me double check. So it's not hugely loaded. It looks like about 25% maybe.
Yeah, so no. So if it's not that, then I guess the other thing that could be going on, and it might be configurable, is there could be some extreme amount of buffering happening somewhere that you can reduce, right, the amount.
Yeah. And that may be part of what it is, because I've noticed that when I put the sensor in 1 frame per second mode, I'm still getting way more than 1 frames per second, like in the order of 5 to 10. So in my program, I'm just going to pull up another one here.
But the other thing, okay, so how are you, okay, you're looking at the display of your Pi through VNC. Yeah, VNC doesn't have that much delay.
Why did this one off? Because it's not plugged in. Why am I not getting a second display?
Did you say that's only 25 pixels square?
Yep. Yeah, that's an
25
option.
by 25 is the sensor. Yeah, I've got it blown up pretty big.
You can do 100 by 100, but it's a lot more data.
So I've got two images there, left and right. And they are definitely, the one thing I noticed is the two sensors interfere with each other. So when I do that, so I need to make sure I have enough separation and that the field of view is not conflicting.
Oh, maybe one is seeing the other's dots.
Yeah, is what I think is happening.
Yeah.
So I've got a left and a right up there right now. So the right is on the right side. The left is on the left side. I'm running two of them. And my CPU utilization is, I don't know, maybe 40%, 50%, 51%.
It's weird. There's different kinds of smoothing on the, or anti-aliasing, smoothing on the output image.
Yeah, there is. So the one sensor is by 25 by 25. And the second sensor, for whatever reason, is not picking up the 25 by 25. So it's running at 100 by 100.
Ah.
And if I run it with the 25 by 25 mode, it picks it up, but it seems like one of them is stuck in 25 by 25. The other one keeps reverting back to 100 by 100.
The lag the same across both of them?
I would say no. When you mention that, no. So the right is actually, I would say maybe a quarter-second lag. The left is the one with the big lag, and they're both running the same program.
Increase the resolution.
Yeah.
Never thought I'd say that as their optimization step. But
Well, the one on the left, you have it artificially kind of scaled up, right? I mean, can you just not do that? Just display it at its native resolution?
I can try to set that to its native resolution.
And I can't imagine that making a difference, but
I was kind of surprised you use such a slow baud rate. Why not use a faster rate and see if that's maybe part of the delay?
115 kilobaud should be fairly.
what? Oh, what? Okay, so where does the baud rate come into the picture?
It transfers the image serially.
It's a serial image.
Okay, but is it
Through the Pi.
Is it okay? On the Pi, it's a USB port. What's on the other end? Is it an actual UART or is it a virtual serial port on the other end as well? And I'm asking because if it's native USB on both ends, the UART, I mean, the baud rate it doesn't come into the picture. It's like USB wire speed, right, that you're transferring at. But if on one of the two ends you have a real UART, twiddling some real bits on a wire somewhere, then obviously the baud rate will make a difference.
Well, both sensors are available. Both the UART and the USB are available, and they are available separately. So I can enable the LCD display. I can enable the UART, which is like the quick connector UART, and I can enable the USB UART essentially. All three are separate. So I can disable all three. I can enable all three. So it treats, for some reason, it's got the screen as part of the setup, but you can enable or disable the LCD screen. You can enable or disable the USB, and you can enable or disable the UART.
Yeah, okay. I suspect there's a real UART. Okay, so the baud rate then could be a limiting factor too, right? I mean, how much data
Yeah,
are we moving?
They have the maximum baud rate at 3 million in the code. And I haven't even looked where it's used. So they're not even using the max baud rate in here. So I'm using 115.2.
Yeah, when I hooked it up to the OpenMVH7, I forget exactly what it is. It's like 900,000 baud, and that seemed to work pretty good. But that was through the actual, the separate pins, the UART, not a USB UART.
Okay.
And I was doing 25 by 25, so it's only 625 bytes, whereas the other is like 10,000, I think, 100 by 100.
What is that?
Yeah, 10K bytes, bytes. Or pixels or whatever.
So this guy is still coming through 25 by 25. Even though I set him to another one is
So those are two completely separate OpenMV M7s.
they're not open MVs. They are max sense.
Oh.
010s.
A010s.
Yep.
They're about $30 a piece US, I think. Figure out why my one won't drop back down to 25 by 25 or 100 by 100. So I believe that's my command to go to 100 by 100.
Yeah. And if it's actually,
Are you saying something, Ray?
oh, yeah. When I did it with the OpenMVH7, I was sending just a single byte. It's, not the colorized version, which I think takes 3 bytes per pixel.
Yeah, this is not the colorized version. So I take the where is it? I plagiarized most of this. I take the black and white image
Oh, you
and
do?
I apply a color rainbow to it.
Yeah,
Color
okay.
rainbow with closest colors I could get back to the original demo program they had.
Yep.
And then I blow it up to display it with you guys, 400 by 400. Otherwise,
Yeah.
if I leave it as it was, it can be
Very small image.
if I leave it as it
Square.
was, 25 by 25.
Heck, you may not even see it on the screen. It's so small.
There is
There.
my image. If you guys can see that.
Yeah. About the size of your cursor now.
You can grab it and move it. It's just a little tiny thing right down in the corner here.
Now,
Does
are
it
you
look like the
talking-
delay is still as much?
Yep.
Huh. That is bizarre.
So it's something I'm doing with that sensor. Something's going on with it. I'll have to see what's happening. So, well, this guy here gives me way quicker in the corner here still, if I'm using the right sensor.
Oh, at 100 by 100 or?
Well, I'm displaying it 25 by 25.
Oh, okay.
Um, leave it as that for now. But that's just where I am at with this. I was expecting more results like I was getting from the right sensor. Fairly quick. You can deal with a quarter second of a lag for most of the instructions you're going to run into. And I don't even need all that. I wish I could just say, hey, give me the closest pixel, the closest thing you've detected and work it out from there. But that's where I am with OpenCV and this thing here. So they do have the routine, the library, the MetaSense library seems to work pretty good for pulling the image. And it's written in Python. You can see what it does as well.
Did you ever hook it up to their IDE?
I did. And running on Linux, it wasn't fun. I tried it on Windows. I got a little better luck on Windows with it. But that's where I sort of gave up on their IDE for it, which you couldn't do anything besides display a picture anyway.
Yeah.
And so I said, okay, time to start programming and see what I can do with this thing.
Yeah. Did you notice the lag there?
No. And for the most part, I did not notice the lag when I was doing it in displaying the binary image. I just showed like what I was getting. But when I displayed not the binary, but the byte image that I was getting back, it appeared to be tracking like fairly quickly at 25 by 25. So it's something that's going on with that sensor. Now that you guys have pointed that out to me with the difference between left and right, it only makes sense. Maybe it was the lightning storm the other day.
Yeah, that's possible.
So that's what I had anyway. That's been my trials and tribulations trying to get a couple sensors working with a big enough field of view.
I thought I have something I'd like to talk because Pat helped me on this, and I was taking a different approach. I wanted more like what he showed us last week, which was the actual pixel values being shown up. So if you guys will bear with me, I'm going to try and to show you what I took. I took Pat's code, made a few minor, because I'm not a Python guy, and I made a few minor changes, and I got a format that I think I can use for because you get your hands on the pixels, you know what I mean? So let me see if I can share this real quick. I'm going to have to change to my Pi, so this is good. I'm using a KV switch, so things are a little weird. Let's see if it works.
Has anybody thought about looking at just one line of the image to say, okay, pretty much it's like a LiDAR and or I guess a 2D LiDAR, and you could evaluate, in the case, either 25 or 100 pixels and say, in the front of the robot, the center of the field of view, is there anything that close to the robot?
So that's what I was trying to do. And with the image that Doug is presenting, I was trying to look at the same thing, pull it into a NumPy array, and then do a region. So where you would look at specific rows and just say, 3 rows high or something, give me the closest value in that area.
Yep.
So, but it becomes, if you're looking at 6 inches above the ground, and there's a branch at a foot above the ground, and your robot's that tall, you're going to hit the branch.
That's
So
true.
then I was going to break it into let's say 16 areas for into a grid, a 4x4 grid, and find the closest grouping in that grid, and just to return those 16 bytes. Doug, did I cut you off? We can't hear you, Doug.
Yeah, I guess the other thing you could do is look at us, maybe 3 or 4 lines, say, bottom, beneath the center, above the center, and at the top, and see, for branch detection, if you're cruising along. Yeah, I guess you don't have to look at the whole image. So
Yeah, and that's where I was hoping that, once you get into NumPy or OpenCV, that you can do, extract regions and just do a quick calculation to see where it is.
Yeah. Did you guys see the screen that I showed or tried
Nope.
to show? Okay. Anyway,
We did see a screen with your byte values.
that's right. That's what I was trying to show, because like I say, allows you to get into the actual pixel values where you can do regions of interest and whatever you want to do. And I think because it's not drawing video, I think it might even be a little faster. So I'm thinking this is kind of a cool sensor. I'm really pretty happy. I mean, for $39, it's really nice. Now the big thing is I haven't taken it outdoors and seeing if I got my 2.5 meters. That's the next big thing. In the house, it's no problem.
mhm.
But in the outside, in the real world, we have to find if we can actually see the,
Yeah.
you probably want to see a meter and a half. Because one of the approaches that's alternative to what Paul is doing with his bumper and what I have on my machine, which is a bumper, is that you can use, the depth camera to act as a bumper if it's reliable. So we have to see, because if this is reliable, I mean, you could simply look for any region that had, close-up values in it, and you say, "Whoa, something's out there." Okay, and then you could go by the row columns, and you could get an estimate of the what's the word I want to try to say? Otherwise you could sum up all the elements in a column and then use that distribution to tell you roughly where the object is, because you got a field of view, X numbers of degrees. So if it's in the center of your screen, it's in the middle. And if it's off to the left, your distribution would show it was off to the left. So you could do a real quick, hey, do I have something out there? And how far away is it? And that would be useful for probably touching a cone. Or the nice advantage of this stuff too is, since it's got so many individual sensors, you might it'd be real interesting to aim this, Pat, at a chain link fence to just see
What you got?
what you got.
Once I can reliably pull data out of it, and that's my next step, is to see, okay, what does it look like when I'm looking at a leafy bush? What does it look like when I'm looking at a chain link fence?
Yeah.
Because like I say,
what's it look like when I'm looking at the side of a transport tire on the highway as I'm about to be crushed?
Yeah, but I don't think you want to try to over stress, like oh, I'm looking at a tree. You
No.
just want to know you're looking at a obstacle that's X feet and it's over to the left, and that's all you need to know.
Yeah, and what I was trying to do is looking at is to pull like take a 25 by 25 image and turn it into whatever. Let's say a 5 by 5 a 5 by 5 image, and
Yeah.
take all those regions of interest in the 5 by 5 image, and just find grouping and say, hey, there's something in there that's 300 millimeters away, so flag that as being close. There's something in there about a meter away, flag that as being medium distance. And
instead of grouping like that, which I agree, I've done things like that, but I'm thinking with a 25 by 25 array, it's already manageable. Do you know what I'm trying to say?
Yeah.
I think you just literally take the, like I say, the sum of the, the average column value or the medium column value, and just, and if you want to look at it horizontally, you look at the rows, you know what I mean?
Yeah.
And tell you roughly where let it tell you where the areas of interest are. Okay. And don't worry about, well, it's in the, the 6th block up in the 7th block to the right, I mean, just, I don't know. I don't think you have to go that far. Okay. All right. I'm going to, I know a lot of people are planning on seeing the debate. I know I am. So I'm really enjoying the conversation, but I'm going to have to cut out early because I want to see this thing. I don't
Got to
know.
record it.
Well, that would be cool, but that's assuming a certain level of technical sophistication, which on mine I don't have right now.
Yeah.
So,
you'll have the next 3 weeks to watch it.
well, that's true. Yeah.
That's all right. We have a little bit of a queue going, and I know like Paul was going to drop out, and a couple others were looking to drop out.
Okay. Well, if I'm not the only one, I think I'm going to do it then, guys. Thank you, and I'll see you next week. Bye. Oh, and for all who don't know, I'm going to spill the beans. Congratulations, Dave. Okay. Bye-bye.
Okay, Dave. So you got to let us in on the little secret here.
The secret is that last Saturday I got married.
All right.
Congratulations.
So
Yeah.
even 80-plus-year-old farts can get married.
You lined up with all the proper medications, the Cialis and the blood pressure medicine and all that stuff.
That's good. I'm happy for you.
Where are you going for honeymoon?
We're going to Salt Spring Island, which is off of Victoria up in British Columbia.
Oh,
Great.
Been there. Very nice
We're
place.
going this weekend.
Oh, good.
So thanks.
Enjoy it.
Will do.
Pat, if whoever's running the list, if it gets short, my apologies for joining late, but I have a bit of stuff I can talk about if you wish later on.
Well, we had you at the front of the list.
Sorry.
We volunteered you because you weren't here, so we volunteered you to do that. And if you want to kick in now, then that's fine. Otherwise, we'll carry. If you're not ready, we can kick in with Mike W.
Nope. Whenever you're ready. If you want me to go now, I can.
Can I put out? Kareem dropped off the list. Mike, I'm assuming you're still good to go. You're not going to be dropping out for the debate?
Multitasking.
Okay. And John, are you okay to keep on the list and let Tom go first? Okay, Tom, go ahead.
All right. For those of you that were here last week, you may recall I mentioned I was working on a.
United States Supreme Court with the intention.
uh-oh.
Okay, Mike, it's all right. Mike muted himself.
that I had mentioned I was building a pulse width modulation to pulse position modulation converter that works with my little radio control system like this that I'll control my outdoor robot with. That's all working really, really well. I'm quite happy with it. So a few days ago, I started to hook it up to the ESP32 on my robot in order to see what would happen. So I'm going to share now. It sounds like some of you read the email I sent out last night. So you have a little bit of, let's see, I think that's what we want. No. Yep, share that. So you have a little bit of a clue as to what's coming along here. But I thought I should put together some rational notes to discuss. The little diagram in the upper left simply illustrates what the position, the pulse position modulation stream looks like on the upper half of that scope display. And that's taken right off of the device that I built to produce this. The lower trace on that scope display simply shows the channel 1 traditional pulse width modulation pulse. And it shows how the width of the pulse, which is about 1,500 microseconds, simply maps directly into the distance from the leading edge of the first pulse to the leading edge of the second pulse. The second channel from the radio control receiver goes from the leading edge of the second pulse to the leading edge of the third pulse, and so forth. In my case, there's only 3 channels, so there are 4 pulses. So the testing I started a couple of days ago was simply to take the pulse position modulation reader class that I have in a very, very simple Python routine that does nothing but read this stuff and display it to me, just like the little diagram on the right, which shows the columnar text data plus this is the Thani IDE, so this is Thani's plotting tool showing the data. This was supposed to work really, really well. And based on the really simple test, if you look at this bottom left curve, it's not bad. This curve simply is created when I take one control on the transmitter and I rotate it from one extreme to the other extreme, back again, and then let it go. So you get this very simple blue trace. The other 2 traces are straight lines because I'm not moving them at all. So that kind of looked okay, and I was pretty happy. But the next step was to take the pulse position modulation reader code and this very simple test stuff and stick it into the main program, which I'm slowly building up as I add the modules to my robot and start testing them and get all the drivers installed and running and a bunch of other stuff. It's what I call the full test or the full robot program. So I did that, and I got the picture on the right doing the same test. It doesn't look at all like the picture on the left, ignoring the fact that the plotter's auto scaling is different in both cases. You can see that it's very noisy, it's very erratic, something's really seriously wrong. Let's go over here. Just to give you a flavor for the code, I mentioned that the one on the left was done with simple test code. The upper third of this page shows literally that simple test code. All it does is it invokes an instance of the pulse position modulation reader, which will be reading on input GPIO 23. It's looking for 3 channels, and the channels have to have a minimum width of 500 microseconds. Once that is invoked, then the logic will simply read the resulting data that's being collected by the interrupt response handler 5 times a second, and it will display it. And then once it's displayed, I can plot it as well. So it's literally that simple. But it's worth looking a little bit at what's inside of the class, the function that is instanced to make this happen. I'm not going to show it all to you, but I'm going to show you the relevant parts, including the additions that I made to it today in order to be able to provide some much more interesting testing, which I'll show you in a minute. First of all, the initialization code, very simple stuff. The first line with the 3 asterisks, I simply create a test pin, which is pin 2, which is an output on which I'm going to output a very short test pulse. The second line simply creates the pin, which is the input pin, which the pulse position modulation stream will come in on, which is passed to the class when you invoke it. And the third line simply sets up the interrupt request. And it says, watch that incoming signal for rising edges. And every time you see a rising edge, go run the interrupt handler. Now, the interrupt handler, I'm showing you the very first part of the interrupt handler, but there isn't a whole lot more to it other than some error detection. The first 3 lines I added, and they're intended, first of all, to set the test pin, then wait 10 microseconds, and then reset the test pin. So what that does is it will produce a very short, roughly 10 microsecond pulse on pin 2 as soon as the interrupt handler is invoked, every time. That becomes a very easy thing to look at on a scope. The next 3 lines are the core of the interrupt handler routine, which simply says, find out what time it is now and subtract that from, or subtract from it the time I got the last time I ran. So that'll give you the differential time, which tells you how much time there is between successive pulses. Very, very simple stuff. That's the essence of the handler. This stuff is all done using integers. There shouldn't be any heap issues or garbage collection issues associated with any of this code. Very, very simple, hence the simple test code. Now, when I proceeded to run this thing in my full robot testing suite, I'm not going to show you the whole code because there's a lot of stuff in it because I've accumulated a lot of test information. But just to summarize, the full testing code essentially consists of 3 asynchronous I/O coroutines. I'm using async I/O as a means of providing some cooperative multitasking to provide 3 different time bases for threads within, not threads, for logic within MicroPython. So there's a switch debounce loop, which runs every 10 milliseconds. All that does is it reads 1 byte of data over the I²C. And it takes the data that it gets and it runs it. It stores it basically into a 5-element byte array, along with a little bit of additional logic, which is used to do debouncing. This logic is stuff that comes from a guy named Gansel. Some of you may have heard of him before. You can go out to his website. You can look at this code and its invocation in C. He's a very, very smart man who's been doing embedded software development, I think, a lot longer than most of us have, and explains it incredibly well. So this is one of the best and fastest debounce logic algorithms I have ever seen. And it does multiple bits in parallel. So it's extremely good, and I use it. The whole thing probably runs in about 10 instructions. And that's all there is inside that 10 millisecond loop. And it's all integer, so I don't think it's creating any problems for me. So I let it run. The second loop is what I call the main task loop. As I develop the robot's software modules, this will grow because it's where most of the code will be that executes sequentially. Right now, there's only a few things in it. The first thing it does is it reads the battery voltage on board the robot, and it linearizes and does some simple exponential filtering of the battery voltage. The funny thing about ESP32s, it has a somewhat complicated A to D converter hardware package, and it's also not very good. So you have to linearize and do a few other tricks in order to get clean voltage readings off of it. So that's all that does. It's still very, very simple code, and it gives me a voltage reading, which is stored in a global array. I'm sorry, it's stored in a global variable. The next thing I do is I read the radio control channel with values. There's 3 of them, and they're integers. So I read those 20 times a second. I simply ask the ppm function to give me whatever its latest 3 values are. Very simple stuff. Because the last thing I tested before I worked on this ppm stuff was the motor speed controller, the motor test logic is still running. But it's very simple. All it is it monitors the push buttons, which are being read by the switch debounce logic, and it uses them to increment or decrement a counter, and then the resulting counter value is sent out to the logic that controls the H-bridge that drives the motors. Very, very simple stuff. The motor speed output logic simply controls 2 pulse width modulation outputs and 2 GPIO pins. Again, I can't see anything in there that would cause a problem, so I left it in. Finally, there's a third loop, which I call the diagnostic loop, runs 5 times a second. It's the place where you normally stick the things where you're trying to figure out what's gone wrong and you need a way to get stuff out of the computer without overloading it too much. So I run this 5 times a second. Right now, it only does a couple of things. It prints the radio control channel width values, the 3 of them on a row on the shell. And it also outputs 1 page to my LCD display. 1 page is 2 by 16 characters. And it uses a package to drive that LCD display over an I2C interface. The only things it's displaying right now is a hello message and the battery voltage and the state of the debounced switches. I like to have that as kind of a boot up page on my robot so I know what's happening when it runs. So that's all. That's what's in this very, very complicated robot test code. There's not a whole lot to it at all. It's also worth mentioning there are a number of instantiated classes, not all of which are doing anything at all. There's 2 pulse width modulation drivers. There's 2 radio control servo modules. There's the PPM reader, which is the subject of this discussion. There's an I2C interface. That also has a PCF 8574 IO expander hooked up to it, so there's a driver for that. There's the I2C backpack-based LCD display, and there's the very simple ADC driver. So those things are all installed, and I left them all installed, although most of them are not doing anything. So the ones that are associated with interrupts would be, but the rest aren't unless they're called. And only a few of them are being called. So that's what's in the so-called complicated test routine. The one that produces this problem when I'm testing the PPM reader. It's important to know that there's a difference between them, but the real story is, I mean, there's not a whole lot of difference. So what on earth is going on? When I was doing my research a few days ago, I ran across a number of discussions of this exact topic in both the issues and the forums associated with MicroPython. Those of you who had a look at the email I sent out, I provided the references to several of those. And I stuck to the threads which were written mostly by the lead developers of MicroPython, since I suspected that they know the most about this and certainly did an amazing job of the analysis of the problem some years ago. I wanted to know what it looked like today, hence my interest in modifying the driver to provide a little bit more of an output signal that allows me to provide the same kind of testing, which you may have seen if you looked at the scope displays in those threads that I referenced. So let's make sure we're looking. So there's the first one. This needs a little bit of explanation. This is simply a screen snapshot from my scope, my Hantek scope. In the top quarter, what you're looking at is 2 signals. The blue one is that channel 1 radio control pulse width modulation signal. The entire width of this scope line is about 5 milliseconds. The width of the channel 1 signal is about 1500 microseconds, 1.5 milliseconds. The little yellow lines, this is the other channel on the scope. The little yellow lines represent those little tiny 10 microsecond pulses that I put code in order to produce. So we now see a signal that's representative of the pulse position modulation stream, and we see the resulting 10 microsecond timing pulses that I'm outputting. They're a little hard to see here, and I wasn't sure what to look at, so the bottom 2/3 represents an expansion of the upper traces between the 2 timing marks, between this timing mark and this timing mark. So that gives you a better feeling of what we're looking at. I've also turned on the electronic equivalent of phosphor retention, so that we're going to see multiple images, multiple successive images on the screen to see what's happening over time. So the blue one is the leading edge of the channel 1 pulse width signal, which is identical, exactly identical, within 1 or 2 microseconds to the leading edge of the first pulse in the pulse position modulation stream. The reason I'm not showing that, incidentally, is because when I was fiddling with my interface, to hook my scope up to it, I never really designed it to be to be accessible to a scope. So I took the only signal I could get my hands on. So it turned out that it was easy to get the channel 1 pulse width modulation output rather than the pulse position modulation stream, which was going to be much harder to get at. but it is identical in terms of where the leading edge is. And I have other testing on the device I built that demonstrates that quite clearly. So if everything was perfect, we would see one 10 microsecond wide yellow pulse right here. It would start as soon as that blue leading edge occurred. It would run for 10 microseconds and then it would drop. But this isn't the real world. This is MicroPython. And what I'm learning is MicroPython is a whole lot different from the real world. Remember, this is the simple test. The only thing that's happening is we're reading the signals from the PPM display and we're outputting them to the shell and to the plotter in terms of execution in MicroPython. And what's happening is with the retention that's happening here, we're seeing, I believe this was set to show 8 traces. So we're seeing, first of all, the pulses are delayed from the leading edge by approximately, I wrote it down here. Whoop, no, I covered it up. If you read the text I typed in at the bottom 2/3, the bottom 3/4 of the display is 30 microseconds per division. The response lag to the dominant leading edge of the yellow curves is about 45 microseconds. And the variation across that set of 8 10 microsecond pulses is about 40 microseconds. So the response, that is the very first thing the interrupt request handler does after the leading edge of the pulse, the very first thing it does is output this pulse. And those pulses are between about 30 microseconds and 70 microseconds behind the leading edge. So the initial IRQ happens in hardware, and the reality is that in MicroPython, nothing else happens in hardware. Everything else happens in software. So after doing some more digging into this and reading those forums I mentioned, it turns out what happens is the MicroPython environment runs on top of apparently free RTOS. So when an interrupt occurs, the details, the parameters associated with a hardware interrupt are packaged up and turned into an application, and that application is dropped into a scheduler queue for RTOS, the free RTOS, to execute when it gets around to it. That's why these things are delayed. Now, they're not delayed a whole lot because nothing else is happening, but they are delayed, and that's the reason why they're delayed. The MicroPython developers refer to this as soft IRQs. They also refer to hard IRQs, but there is no hard IRQ implementation available in an ESP32. There are on several of the other computers, small computers that they've implemented it for. For example, the Pico has a hard IRQ implementation. Based on the reading that I've started to do on how well that works in the Pico, it actually doesn't work much better than what you're looking at right now. So that's kind of disappointing. I don't know why, but it's not much better. So even the hard IRQs are nowhere near as good as I'm used to when I code in C++ on an 8-bit Arduino, which is how I implemented my little PPM encoding device. I wrote it in the Arduino IDE, I wrote it in C++, and I'm running it on a DigiSpark, which is just a little tiny Arduino, an 8-bit or an 8-pin Arduino. I'm getting about a 2 microsecond lag in the response on the code I wrote on that Arduino. And it's, it's running at 60 megahertz, but it's not very powerful. It's nothing like the 240 megahertz, which this ESP is running at. So it's a little disappointing. Now, this is just the simple test. Okay, so in the simple test, we're looking at 45 microseconds nominal variation and maybe another 40 microseconds variation around that in terms of what's happening. We're trying to use this logic to measure pulses that vary between 1,000 and 2,000 microseconds. We're already out by 10% of that. Well, 5% of that anyway. That's usable. The problem is this is on an ESP32 that's doing nothing else. So let's look a little further. Here's the same test results, a little different format. So I'll describe this a bit in a minute. This is the same test running on the second of the MicroPython programs that I'm using, which I refer to as my full robot test, which really isn't much of a full robot test. There's a little more happening. Again, I didn't bother with the expansion of the full interface. I just thought I would show this the way it is. The blue trace, again, is the channel 1 pulse width modulation signal. So from the leading edge of this blue trace to the trailing edge is about 1,500 microseconds. The entire width of this display is 10 milliseconds. The yellow traces are, as we discussed before, they are the accumulation of the 10 microsecond timing pulses, which are coming out of the interrupt request handler as soon as it's invoked every time. Now, when you do the same math, I won't show it to you now, but when you blow this up and do the math, geez, every time I move my mouse, I call up that little toolbar. The response lag to the first cluster, you can't see my hand, to the first cluster of those little yellow things is about 150 microseconds. The variation across the set of 10 microsecond pulses, which are above the blue pulse, which represents the first measurement, is about 1,000 microseconds. Remember, we're trying to measure a pulse that's only 1,000 to 2,000 microseconds long. And here we've got 1,000 microsecond variation in a short set of samples of how fast the interrupt request handler runs. The reason there are more yellow pulses here is because there's not just one pulse being responded to, there's a set of 4 in the PPM stream. So this block represents the responses to the second pulse. This block represents the responses to the third pulse. And this block represents the responses to the fourth pulse. So this thing is pretty consistent, even in this relatively small sample size I'm working with. In terms of the objective of measuring very relatively short pulses reasonably accurately, this thing is a massive failure, unfortunately. So I'm kind of disappointed. I'm not sure what to do about it. Not only am I interested in the PPM encoder input processing, I also have an ultrasonic sensor, and I may add some more. Ultrasonic sensors, of course, also require pulse width measurement. They require sending out a 10 microsecond pulse, which probably will work okay. But they also require that you read back the width of the pulse. I'm not sure how accurately I can measure that. 1 centimeter is about 54 microseconds. So I'm not sure how much of a problem I'm going to have using an ultrasonic sensor for any kind of accurate measurement using the capability inherent in the ESP32. I suspect none at all once this robot's computer gets busier and busier. I also need to do wheel pulse counter counts because I added wheel encoders to the wheels. They're relatively low resolution, so I'm only looking at about 10 microseconds or 10 milliseconds worst case between pulses from the wheel. That wouldn't be a problem here, but there is a plus. The ESP32 has a block of 16 dual input hardware counters designed exactly to measure quadrature encoders in hardware. That's kind of cool. And the MicroPython people have done a partial implementation in support of that capability. It's not a full quadrature counter. It's a single pulse input counter. Fortunately, I only have a single pulse output on my set of wheel encoders. So I'm going to give that a try later this week and see how well that works. But I still have this PPM encoder problem. And if I use the ultrasonic encoders, I will have a problem with those as well. So I made up a quick little list of what things I might possibly do, which might be of some interest to you. Of course, I can stop using MicroPython. That may be the simplest answer. I can see whether there's a way to access the hardware interrupt request on the ESP32 outside of MicroPython. But I've been looking for anybody who has hinted that they've done that, and I'm not getting any hits yet. I can also try switching to the Pico, which does have a MicroPython supported version of hardware IRQ. But the early indications from my searches are that it doesn't seem to be that much better. It's probably worth testing just to find out where it sits, but I don't know. The third point is garbage collection causing a problem. I do not think so. There's virtually nothing happening in the code I'm running that would force any degree of garbage collection, and certainly not enough to create the massive and continuous problem that I'm seeing when I do my testing. I can do all the fast logic on external devices. In other words, offload this stuff to peripheral processors. I suppose I could. My Digisparks won't work. This will take at least a full 8-bit Arduino and maybe more in order to do this properly. The problem then will be getting the data from that external processor into the ESP32 in a reasonably timely fashion. Digisparks don't do that very well because I have other experience with them. One of the problems may be deciding just how to get it in. UARTs are not a good choice on ESP32. There's only one available hardware UART for application purposes, and I plan to use that for the GPS that I've put on the robot. So that leaves me with considering I2C or SPIs. I've had problems with those in the past, but only under power on conditions, where two small processors sometimes have trouble getting their I2Cs to synchronize. And it takes an extra hassle to get that to work in the code. So I may or may not do that. I don't know that there's any other ESP32 hardware peripherals that can help me with this problem. I've been researching the all 732 pages of the ESP32 datasheet, the technical reference manual. I don't see much in there in the way of usable timers. I learned about pulse counters, and I'll try that, but it won't work with the PPM unless I add outboard hardware. And I don't see anything else in those familiar classes of peripherals. What I did discover, and I'm not sure how many people know this, there is a complete second microprocessor inside the ESP32. It's 8 bits, it runs at 8 megahertz, it's got access to 8K of RAM, it's got access to all the IO peripherals. It's known as the ultra low power coprocessor. And you can place code in it and execute the code like you would with just about any other 8-bit processor. And it doesn't have its own operating system. MicroPython doesn't know anything about it. And I kind of looked at that. I'm going to see whether anybody's tried that. I've been reading the chapter that describes how to use it. Unfortunately, for me to develop it from scratch would be a non-trivial problem. So I don't know how motivated I am to do that. But it certainly looks very, very interesting. You can access all the hardware. You got lots of room to write code, and it runs at 8 megahertz. And it has a dual ported 8K block of RAM. So the ESP32 can access it as well. So moving information back and forth between the two of them is really easy. Anyway, that was kind of a novelty, but I don't know whether I'll pursue it. There are techniques to improve the execution speed of the interpreted byte-oriented MicroPython using MicroPython native implementation or Viper implementation. I don't believe either one of those options will make any difference with the problem that I'm seeing. I can see how they could help with other problems, but not with this one. So I don't think that's going to be of any use. There are ways to access the hardware registers of the peripherals directly from MicroPython, but I don't know whether I'm allowed to write an interrupt response handler that bypasses the MicroPython logic or not. I haven't pursued that far enough, but I was quite interested to find out that in MicroPython, there is a library you can import that lets you know where all the hardware registers are and gives examples for how to access them directly. So that was an interesting choice. I don't know how it helps me yet, but we'll see. There's also some discussion. Robert H.H., who also appears as H.H. Robert, is one of the lead developers in MicroPython. And he did point out that you need to watch out for flash memory cache misses. But I think that's only going to happen if you're running a lot of code, such that you are required to reload the code from the flash memory because you've consumed far too much of the available directly accessed RAM in the ESP32. I don't believe that's happening, but he did say that if it occurs, it can slow you down a lot. But it's not going to happen very often, and it doesn't account for the fact that I'm seeing this problem so frequently. That's not an SPI flash memory cache miss problem. That's all I could think of. Anybody else have any thoughts?
Well, I think, I mean, you have a lot of possible fixes already on here, but I would say just fundamentally the idea is flawed. Like the idea, the idea of using Python to measure, pulse position and or width and counting, at almost single digit microsecond level. It's just not what Python or MicroPython is designed for. I think, I think it might work in some situations, right? But I just think you're pushing the limits here of what this stuff can be used for. It's almost like, I mean, I'm not a big user of MicroPython, so I can't. Yeah. But sort of the analogy for me would be, I'm being a big proponent of Linux. It makes sense in a lot of cases, but I wouldn't try to use it to measure things down in the single-digit microsecond space, right?
That is eminently clear at this point. Yes, sir.
Yep. So it's fundamentally flawed. Now, could you fix it? I suppose you could, right? I think implementing something in a native fashion would be your way out of here, right? But it gets, if you're gonna have to get pretty comfortable with how MicroPython is implemented on the ESP32, you'd have to find a way to create a native interrupt handler and pretty much bypass everything else.
Not going
there. That might work in the end, but even that would only work if there's no other stuff going on that disables interrupts for too long, which you don't have control over, right? You can potentially minimize and almost get to zero the sort of overhead associated with handling the interrupt. But delays because interrupts are disabled for other reasons, well, those kind of delays are still going to be there, and who knows how big those delays are. So again, the concept is fundamentally flawed. This is not designed to measure these kind of pulses in software, right? You're not tapping into a hardware feature here, which of course, if you're able to, and you have it on your list here, that's what you'd want to do. But doing this in software, this is hard on anything except, bare metal set of microcontroller.
And that is where I suspect I may go, yes.
I mean, you could like enlist the help of a little coprocessor, right? Let's say you want to keep doing most of the work on the ESP32 in MicroPython for a variety of reasons, but stuff like the PPM processing, right? Maybe that goes into a little 8-pin AT-tiny microcontroller, right? That spits out processed information over basically a UART type signal, right? And then you're feeding that into a serial port on the ESP32. That's how I would approach it, and I've usually done it, right? This kind of very low-level stuff. I don't even try to do it on the Raspberry Pi and Linux. Just do that on the microcontroller.
And I've done that with other projects I've worked on that had coprocessors. The problem with the ESP32 is it only has one hardware UART, which I'm already assigned to other purposes. So I'm stuck looking at whether I can make it work with a software UART, which I am reluctant to consider at this point, given the problems with MicroPython. I don't think the software UART would work very well either.
So maybe the ESP32 is just not a very good processor.
Yeah, that's a little bit of where I was headed to. I hate to say it, but or maybe an ESP32 with MicroPython. An ESP32 with C++ might be a fabulous little box.
I've got a suggestion for you, Tom.
Yep.
Teensy 4.1, 600 megahertz, lots of memory, got an SD card reader, and it's got multiple I2C UART SPI ports.
Yep.
So the one thing it's got going for it is the processing speed, but the serial ports, the I2C ports, the SPI ports, it's got multiple on different pins.
And I'll bet you program it in C too, don't you?
You can program it with an Arduino.
I'll bet you program it in C, don't you?
Yeah. Well, it looks like it validated my choice of using a Pico and C++ for my hardware controllers. Yeah.
Yeah, I admit this was a big surprise. I wish John Hyland was here to comment. I'd love to hear what he has to say, but I know he's not. Okay, well, thank you very much. I hope that's helpful to you.
Well, thanks, Tom. I was just looking. I've got a teensy sitting on my desk somewhere here, but
Yeah.
No,
But
this was helpful because now we'll know not to do this.
well, and that's what I mean, or do it, but be very, very aware of where the limitations are. They're a lot worse than I thought they were when I started down this road. I still really love working in the MicroPython environment, but it's not going to handle this kind of high performance real time problem. It's just not going to.
well, that's yeah. So when you look at the Pico and some of the PIO stuff that they have, it might make sense when you're reading encoders and doing stuff that it's done in hardware and not in software. You know, to do some of this stuff. And I don't know if you've considered trying to rewrite a routine to extract all the pulses in PIO.
But with all due respect, I could write this stuff in C++ and run it on an 8-bit processor on Arduino, and it would perform incredibly well. The hardware versus software issue isn't the issue. The hardware versus really, really awful software versus really, really good software is the issue. I'm sorry, but the ESP32, 240 megahertz, right? It's got lots of I2C, lots of, curiously enough, lots of ISP. It's got poor hardware UART, unfortunately. It's got 3, but only one of them's available. And that was kind of a disappointment because there's one of them available on an Arduino too. Anyway, if I wrote this in a compiled language, it would just blow so well. But it's not. So I will try that next, probably. I had already configured ESP32s to program in the Arduino development environment. It happens to be the one I'm familiar with. I know it's not the best choice for compilers, but I'm very familiar with it, and I may try this next there.
Uno R4 has 2 separate serial ports, one USB, one serial.
Probably because it doesn't run on MicroPython, right?
Doesn't run on MicroPython. And
Yeah.
I believe, I was just reading, I believe there's 2 I2C ports on it as well.
Yes, there's 2 of them on the ESP32, and there are 2 ISP ports, and there's something called the 2-wire automotive interface, which is another high performance hardware interface. There's a whole bunch of them. The technical reference manual for the ESP32 is fascinating reading to browse through because of all the hardware buried in there. I had no idea, but most of it's not supported in MicroPython for very good reasons. So anyway, it was a fun week, sort of. I learned a huge amount, but I didn't get the outcome I was hoping to. So number 4 or number 2 are probably what I'll do. I'll try putting this stuff in C++ first because the conversion is pretty easy.
Well, thanks, Tom. I have a very minor update. I managed to reset my Make Sense A010 board, and it's in 100 by 100 mode, and the response is very quick. Like I say, about a quarter second, so which is very usable for a distance sensor.
Yeah, it's about 1 frame. That's pretty good.
Next we have, I think it's Mike on the list.
Okay, so
are you available, Mike? Or you want to push off and see if Tom or John wants to go?
I'm here. Yeah.
Okay.
But so I have the so I put this foam on here, and it sticks over the edge by a couple inches, and it cut down the noise quite a bit. So I think I hope it's usable, and also I added this light fixture. I need to bolt it down, but I got a nice 12-volt light fixture. So I need to bolt it down and add it to the power bus. So she'll have a light on her as she's doing her thing in the audience, and I plan to put a speaker on it, a Bluetooth speaker, so she has a voice. So she's doing pretty good. Yeah, but And then on a different note, I've been like, this is a no software project so far. If they want to control the light intensity with the remote, my remote controller, I have to add a little Pico on there to decode the PWM and turn it into a light intensity. But I'm hoping they don't ask for that. So, but so what I'm doing is starting to think about the Robo Columbus for 2025. I hope to show up this year just to manually drive my car around, but I was, my last robot was in used ROS 2, and while I was doing that, I would just I would look into a lot of ROS stuff until I got something to work and said, okay, I know what I'm doing. Okay. and then I'd move on to the next problem and say, oh, I fixed that. And then I'd take what I'd learned and just repeat it over and over again. But what I'm doing right now is starting all over, not all over, but I'm decided to do a course in ROS 2. And so I'm starting to do the Udemy course, UDEMY. Yeah. And I chose that course because it just met my operating style, I guess. So basically use your own ROS on your own computer to follow the instructions. You're not really tied down to their class environment. So I like that a lot. So I'm working on that a lot, and I'm going to go on a cruise, and I need something to do in spare time, so I'm going to do the coursework. So that's basically where I'm at. That's all I have.
Okay, you said that was the course was on Udemy?
Udemy, yeah.
Okay.
Yeah, so I looked at it and said, I don't need that basic course, but I'm going to just see if I missed something, you know. And one thing I did is I sort of looked at the C++ versions versus the Python. I said, I really like the Python version because it looks simpler. And it was simpler. But going through the course, I'm doing C++ and Python. So that if I need some speed improvement, like an algorithm-heavy node, then I can code it in C. But if it's just sort of algorithmic, you know, a bunch of if-else statements, the Python should work fine on the Pi 5.
That's something I'm thinking about as well.
Pardon?
Is C++ on a Raspberry Pi to implement some sort of API that can be used maybe from Python for routines to try to speed things up.
Yeah, so I believe in ROS 2, in ROS, all the underlying code is in C++, because it seems like during the bleeding edge of it, you get your C++ version, and then sometime later you get your Python version. So I think they take the C++ guts and just wrap it in a layer of Python. So you get, I think you can get the speed advantage of C++ using your Python. But if you're doing a lot of mathematic loops and triple loops and a lot of math processing, and you don't have a library to do it, I think Python would start to get real slow. But I've never timed it, but at least I'm gonna have options because I'm gonna learn how to do both of them. Try to be, I don't want to say a master, but at least be proficient in both of them in ROS 2. So
What's nice is Python is so much easier to just go out and make a quick change and do something, and off it goes. You know, C++ or C has got to be compiled and you know, on whatever platform it's running on.
Yeah, even in ROS, you don't have to recompile. We don't have to quote recompile, which is colcon build in ROS 2 when in Python. But if you write a module in C++, you have to do the colcon build step, followed by sourcing a setup file.
And ChatGPT is better in Python than in C and C++, I think. So you can ask for some help.
Ah,
No, and I think that's, for me, that's a real benefit. I mean, there's a lot of times, it's just stuff that there's always stuff we have to Google all the time, right? We don't have all the answers, right? You go to Stack Overflow, whatever, right? I just pose my questions into ChatGPT, or the Copilot built into Visual Studio Code. And it does, I think it is more trained on Python than other kinds of source code, and so it can help you more if what you're doing is working in Python.
mhm.
Never thought of actually looking that up, trying to get ChatGPT to do some coding.
Yeah, don't ask it. Don't ask it to solve the problem for you. Just, again, little things. You just, how do I do this again? I don't remember. How do I use this? How do I use this library? How do I use that feature of Python? It's like kinds of things that you just don't have memorized. It's very productive to get this little kind of help and assistance.
So I should have asked ChatGPT a week ago about my question. Eh?
Yeah, you're pushing the limit of ChatGPT now.
Yes. So in Python and in general on a processor like the Pi 5, when you ask it to do a math operation, like a big vector operation, I'm assuming that that operator is written in like C-level code, and so it's quick. It doesn't. They don't write all those loops down low when you ask it to do like a vector operation in Python. Does anybody know the answer? Because I'm assuming it wouldn't.
That's exactly the kind of question I would honestly ask ChatGPT. It's that sort of question I would pose it. I think the answer is, if you're using libraries like NumPy that are designed for high performance numerical processing, somehow or the other, there's an underlying implementation that's native, right? And you get maximum performance. But if you just write naive Python code, there isn't going to be any magic happening automatically, and I think it's going to just be dead slow. So you got to use libraries that are designed to behind the scenes without you realizing it, right? They do stuff in a native fashion, and you get the performance of the platform.
Yeah,
Right.
well, that's how you manage to do things like in OpenCV with NumPy and OpenCV, that it's not processing, most of the image in Python in the background. It's usually a wrapper around some sort of C++ API that it's brought out to Python.
All right. Thanks.
Well, thanks for the update, Mike.
Mhm.
Next up, we had John.
Okay. On Strabo, I found this thing, so let me find what we're after. Yes. So I found another self-balanced robot, and notice it uses the cheap motors. So I'll run the video because I was actually impressed how well it seems to do it on the balance.
Interesting that the weight is at the top.
Well, after it runs through, I'll step through the actual article because he did a pretty good job at describing it. So he had a couple of comments in there that sort of was related to our discussion on balanced robots. So yeah, I thought it was interesting.
I assume he's got encoders on the top part of the motor.
Yeah, I'll run through the actual article as to all what it has, but the part that impressed me was just how well it balanced in that. So it's considering it and the relatively cheap components in it. speed it up.
Does it use an eight pin Arduino?
So you can see it's so you can see it pretty long, this length. I don't think you edited any there per se. So there's close-up picture of it, and this is what he uses.
Arduino Nano.
Okay. And it uses a wire data NRF, whatever that is. So there's the list. He uses a accelerometer.
So he probably doesn't have encoders on his motors then.
Well, this is what the list is. I didn't see it anywhere. It just says the motors. So yeah, you can get encoders on those motors. I have a couple of those motors that do have the encoder.
Yeah.
Here's his theory. As I said, it was sort of interesting to comment about, okay, where to put the rate, on the top, in the middle, down below, and stuff like that. So, yeah.
Yeah, it looks like he's using the MPU 6050.
Which I assume is hopefully you can get nowadays. I haven't really looked for how hard it is to get the parts. And there's how you use a meter and the gyroscope. And he talks about building the battery. Okay, and that's where he says better to have less, therefore you don't have to tune it as much, was that sort of comment. So there's where he talks about the balance of the gravity. And there's the wiring of it. I know how you're right. There's no encoders on the motors.
Yep. Damn. We'll have to send that over to Harold and see if it's that same code that he's been looking
Yes,
at.
that's what I was curious about. That's why I was going to ask him, and like, hey, is this the library you're using? Is it the the meter scope thing? So I don't think he was using encoders either, was he? I don't remember him saying anything about
Yeah,
it.
I don't know.
So, but there's the library. It talks about the connections and the plane. So it looks like it's all there. So it's just a matter of get the part and put it together. I may actually try this one because it looks like it was balancing well. And then there's his controllers. So it looks like a nice complete package, well map. Even down to how to use the radio on that.
I agree. That's a good find. It looks identical to the hardware I built for my balancing robot, and mine doesn't balance nearly that well.
And then there's another close up of the picture. You can see where he put the things.
He's used 2 different power supplies on board the robot. Did he explain why?
Let's see, where is his power sources?
Its schematic shows he used 2.
Yeah.
218 6050s.
One for the motors and one for the electronics.
Probably.
Probably, yeah. So as I said, looks very well documented in that. So And it talks about, adding the ultrasound to the mix. And what is it for the final thoughts? Yeah, it says bring tune the PA. Pays work. Don't put a print and it will slow down the loop. Set a reason for separate batteries. Noise.
Okay.
It's the reason why. And he's going to change the bore out seemingly. So yeah, I thought it was a well layout article, and it looked like it was balancing very well for all the components. So Harold, you might want to take a look at this too. So yep, that's why I thought might be of interest for people, especially for the two-wheelers.
Well, thanks for that, John.
Yes.
Very interesting. I think a few of them people are interested in that. Can you post the link in the chat?
Yeah, I will.
I think that takes care of our queue. Has anyone got anything else they'd like to discuss or show or question? Stump the club? Oh, maybe that's it. Everybody's going to.
Sorry, one thing that I do have personally, just gonna turn my camera on. So from the last meeting in person at the Dallas Makerspace, I brought this arm here, which is a work in progress. It's a kit I bought off AliExpress. However, one thing that I've noticed that so the way it works or it's assembled is it has some metal brackets like this, and then they're fastened by some nuts and bolts. However, over time they've just becoming like loose to the point where like the arm like is just loose like this. And I'm not sure if there's some kind of hardware that I would put like between the nut and bolts in order to like secure it and make sure that it still stays secure even when the robot moves around.
One suggestion I think I'd have Kyle for you is to use a couple nuts and bolts on each joint like that to basically prevent that pivot action with that you have just one bolt.
Or lock nuts.
Or lock nuts, but if you had two of them, even if one is in the center between the two brackets, but one is farther out close to the end, that'll lock the two brackets together. So they won't be able to move sideways like to spin.
Okay.
I don't know if that's an option for you.
Yeah. I could look into it. But also, is there some sort of like, I think part of it is because there's not a lot of friction between the metal plate and the screw, because there's not a lot of friction between the two metals. I believe that's what causes it to loosen up as the robot moves around. So is there some kind of like rubberish, or is that what the locking nut does?
Well,
lock nuts usually have like a nylon insert in them that the threading is a little off or shifted, and it just prevents the nut from backing off because it actually binds between the metal threads and the threads in the nylon insert.
Okay.
Yeah, you might try two-sided tape.
Yeah, I was going to suggest that as well. is to put a piece of two-sided sticky tape between the two layers, the two metal brackets.
Kyle,
I
can
could
you
try
show us
that.
the joint again that you were describing?
Of course. So this is the whole arm assembly right here, and it's zip part right here. So it uses I'm not sure if it's M3 or M2, but one of those metric type nuts like this, and then its corresponding bolt.
Yeah.
And that's what fastens it
Sure.
into the robot.
Sure. And looking at the joint again, if I understand correctly, your problem is with the joint nearest to your left hand. Is that correct?
Yes. Yes.
And where
Blade
the
right here.
U-shaped brackets are only held with one bolt.
Right. So there are so there's supposed to be two bolts fastened in here. One not sure if I can show it well.
Yes.
So there's on one side there's one bolt right here, and then on the opposite side there's going to be one other bolt.
Yes.
And that's what's that's all that's fastening it, and unfortunately it keeps loosening itself.
Okay, gotcha. So the bolts are coming apart. There's supposed to be two, and the nuts are coming off the bolts on their own.
Yep.
A lock washer, you can get them at any local Home Depot or hardware store. A lock washer, some Loctite, either of those choices will help you a lot. That's really what you should do first. Is
And you
find
don't have to,
nut.
yeah, the lock washer and stuff doesn't need to be metric. Just get one that fits. Yeah.
Okay.
The other one is a nylock nut. If you could find a nylock nut to fit on there.
Yeah,
And
that
they
would be
won't back
metric. Yeah.
Wait, so what's the difference between that and the other locking nut?
Same thing, I think. Yeah, I just used to refer to them as lock nuts. I mean, but yeah, I think, is Nylock a brand?
I'm just looking it up here. Nylock. Just to show them a picture of what it is. I mean, let's say it's going to be a 3 millimeter.
Got one, Mike? Yeah. The little black ring in there is, I'm assuming nylon, but who knows what it's actually made of.
Can you see it, or I can
Looks
post
like
a
the
bigger
far
picture.
side with the big screwdriver and the, you know, for the mechanically declined or something. Yeah,
yes,
that's what they look like, and it's. Yep, there you go.
There's a little bit bigger picture, so that's a larger one, but
Yeah.
you can get them all the way down to, you know, small size. And I'm assuming
Yeah,
your price
Loctite.
is gonna be much cheaper. This is a Canadian site, so your prices are going to be much cheaper than that from Amazon.
Yeah.
I've just dropped a link in the chat that is a primer on fasteners used in small robots, part of the first robotics stuff. Have a look through that chat discussion. You'll get a lot of good ideas on the fundamental basics of what keeps nuts and bolts together in a robot. So I'll put that link.
And you,
All right.
you probably want to use the blue Loctite, not the red, because the red you may break the bolts trying to get it back off.
So what's the difference?
Red is permanent glue.
The red,
Blue is just good glue.
yeah, yeah. The blue typically you can get off, but the red, I don't know how it chemically bonds the parts together or something.
On a the red on a 3 millimeter nut, when you go to twist the bolt apart, it'll probably just snap the head off.
Mm-hmm.
Yeah. So do not buy red.
Noted.
He's got number 22 there.
Yeah, and it says low strength on there. There we go. But so red is it's a red Loctite, but it's called thread lock number 22. But it actually says low strength, so it's not a high strength one.
Maybe they sold you a
Yeah.
bottle of water.
Maybe.
But Kyle, start with a basic lock nut first. If there's no lock nuts on those bolts underneath the nut, what that does is it just provides some friction so that the nut won't come loose on its own.
If you could find a little serrated washer, that would probably do the trick.
Yeah. Now I think the friction from the locking nut is exactly what I was looking for. So I'll try that.
Okay.
Now one other thing, I pull up my notes. I had some things that I also wanted to talk about. Right. So for Onshape. So the last time we went for the personal in-person meeting, we were using like Onshape to create our own designs. And I was wondering like how like that looks to employers versus SolidWorks, because I know that SolidWorks is one of the big programs that employers, especially for like mechanical engineering or robotics, are the huge ones that they're looking for. But for one, is Onshape one that employers would look at and like to the point where like they'd have like interest? And two, if someone was fluent in Onshape but not yet fluent in SolidWorks, how steep is a learning curve to SolidWorks for someone who is familiar with Onshape?
Does anybody use SolidWorks here? Those are all that's in the paid category of software, right?
Yeah.
SolidWorks and the Fusion 360, I think, are primarily what some of the employers are looking for when you're doing design and modeling. Typically, it's out of our realm as a hobbyist. So we're always looking for a good, cheap version of software that we can use. And one of the reasons some of the guys were attracted to Onshape was the price model. For hobbyists, it was pretty much free. Good price for learning. Usually there's good student discounts. I know Fusion 360 is, I believe, free for students. And SolidWorks, I'd be surprised if they didn't have it as well. I know that some of the OEMs that I work with are using SolidWorks. And they're designing, sawmill equipment. So, pieces that, equipment that are into tens of tons and more. And that's typically what they use.
Is there a hobbyist version of software that is more compatible with, say, SolidWorks? That if you learn it, then it's a short learning curve to SolidWorks?
That I'm not sure. I know that the guys did mention when they were doing it that a lot of the features and terminology was very similar on the different softwares. And they had reviewed, I think it was Onshape, and I'm trying to remember what the other one they reviewed.
Maybe that's a Chat GPT question.
Yeah.
Was the other one FreeCAD?
Well,
Maybe it
there's
was
FreeCAD, there's Design Spark Mechanical, there's several out there. And the biggest problem with like the Fusion 360 in that is it tends to be expensive. But as he said, if you're a student, you might be able to get discounts, whatnot. I mean, and that's the main reason why I tend to not use them. I've touched on a Fusion 360 before. And they're very similar in some ways. They have little variants, but it's sort of like learning C, Fortran, Pascal. They all have for loops. They all have print statements. So it's just a matter of syntax is the way I look at it at that stage. If that helps any.
So you're saying SolidWorks is similar to Onshape?
They're all similar. That's why I'm saying it's basically variations, and they'll have a little different code, or maybe they'll present in a different way, and instead of being a 2D type thing that you stretch and pop into 3D, it more of a 3D to begin with. And so they're variations. but the key is getting sort of the root.
Kyle, I think you might be better off to ask that question again, maybe next week.
Okay.
Paul will be back, and I know Paul's been doing some work in it, and there may be a couple others that are off the meeting right now that may be more informative than we are.
Kyle, I'm guessing you're a mechanical engineering student.
Yes,
So you're headed in that mechanical engineering profession direction.
that is correct.
What year are you in?
So I've taken some classes, dropped out for a year or so, and then came back. So like around like early-ish years.
Okay, so that would be the kind of question that you might find you can get an interesting answer from if you ask a couple of your professors what CAD tools they recommend in terms of a forward direction. They're probably a lot closer in touch with what the industry is using than most of us would be.
One little minor comment I'll make on that, though, is realize so a couple of years from now it can change. So, I agree with, talk to the professors, sort of seeing what direction they're going with type thing. Because,
Right.
it does change over the year. I mean, I can tell you in my case, I start off with programming in C. Nowadays, it's, web-based applications, to give you an example of why I said that.
Now, SolidWorks has been around for a long time, relatively speaking, compared to like Fusion 360 and the like.
Yeah, this group is probably too frugal, or maybe we're all tightwads. We don't want to spend big bucks on CAD programs. So
Especially when they're not that. That's why I'm saying they're not that much difference. They each have their niche, and that's why in case of the Fusion that they have their niche, and so hence they charge more because of certain features they have. But those features we don't tend to need, so we don't use them as much. That's, but for, business and that, I agree. The best path is talk to the instructor, sort of seeing where the trend's going and what type of functionality they tend to use more.
yeah, probably what you're going to find is the more people you ask, the more software packages they're using, So,
Yeah, but there are certain ones that tend to concurrate around. So I would agree with you, though, that you ask 10 people, you'll probably get multiple answers, but there will be some that are, it's more along the lines of features and what ones are for what applications you're going to use it for. So I suspect certain industry uses certain ones for that reason. So did that help any, or did we mower up the water more?
Did we answer your question at all, Kyle?
I suppose so, more or less.
I'm sorry we can't give you a better answer than that at this point.
Yeah.
Like I say, next week you may want to revisit that question.
Yeah, I will certainly do that.
Okay, great. Thank you very much for your presentation. Anyway, your robot arm looks very interesting. Looking forward to see it functioning.
Yep.
Does anyone else have any questions for tonight, or are we done? Going once? Going twice?
Sold.
Okay, guys.
Okay.
Thank you very
Bye.
much.
Thank you.
Next week.
Okay. So Pat, do we know if we're going to